Welcome to Unlocking Science. Our goal is to glorify God by studying and unlocking the secrets of His amazing creation. Dr. Minton, what are you doing here today?
We're going to talk about something that's alive that you might not think is alive. Bones.
Bones. All right. So our topic today is going to be bones. I will be following along on Ken Ham's Facebook page. So if you've got comments or questions, drop those in there and I'll be able to answer them for you. So we've talked about this a little bit before, but how long have you been studying the topic of bones?
Well, I taught in a medical school for 34 years, so I was certainly involved during that time, but I did a little studying before I got involved with teaching in a medical school.
Sure, even from an Ivy League university.
Right.
Okay, so we've got a very well-trained expert in this area. You've probably taught thousands of medical students over the years during your career there at Washington University.
Yeah, well, 120 students every year, basically.
Okay.
We started out with a smaller class, but 70 in the first year, 70 or 80 in the latter years, 120. So yeah, I would say a few thousand.
Yeah. And then you've had the opportunity to reach many more through your work here at Answers in Genesis over the last 12 years or so as you've been here full-time working and speaking. And if you're ever here at the museum, make sure to check out one of Dr. Minton's workshops. He does workshops on ape men and the chances of evolution happening, all kinds of great things, so you can check your daily schedules as those things come in. Okay, so our topic today, we titled this episode Living Bones. When you think about bones, do you think about bones being alive or being dead? And when we think about that idea of bones, if we were to find a bone out in the woods, so I'm out hiking in the woods a lot, out deer hunting or fishing, walking down the trail, and you find a bone, it's just a piece of dead material. It's basically some organic matter that's been cast off by this dead individual, or this now dead, once living individual. But inside of your body, that's quite different. Now, we've mentioned before, critters like Claude don't have bones inside of them. They have an exoskeleton on the outside. And that's made out of a substance called chitin. But we're going to be talking about humans specifically today. And humans, as mammals, have an endoskeleton. So our bones are on the inside. And those bones are very complex, and they make up a big portion of our body, and we'd be in trouble without them. So Dr. Minton's going to talk through some of those ideas and help you understand a little bit more about why we think of bones as living things.
Well, first let's give God credit for having created bones. We look at the Bible in Job. Job recognizes that his skeleton is a gift of God. He said to the Lord, "Did you not pour me out like milk and curdle me like cheese?" An interesting expression. And then he said to the Lord, "Did you not clothe me with skin and flesh and knit me together with bones and sinews?" And you might not think of bone as being knitted, but it really is. You'll see it's an amazing weave that we really don't even fully understand. Well, let's consider, what would life be like without bones? Have you given any thought to that? Without bones, you'd look about like that. You'd be a puddle. You know what? Being a puddle would not be your biggest problem. You'd have other problems as well that would be far worse than being a puddle. Let's look quickly at the functions of bones. You'll be familiar with some of these. They're mechanical support. They hold us up. They protect the organs of the body, like the brain and the heart and the kidneys and all the vital organs. They work like levers to get force, to move our body around, to get leverage. How about this for important? Bones make blood. Without blood, we wouldn't be alive. The Bible says the blood is the life. So I would say that ranks right up there with probably the most important thing bone does. Next to this last item that may be a bit of a surprise, it's called calcium homeostasis. It simply means bones are helping to keep the calcium levels in our body constant. If they get too high or too low, that can affect muscle contraction, making them either lock up or become flaccid or weak. So also calcium is involved in cells communicating with one another. They have to talk to one another. And it's the glue that kind of holds our body together, involves calcium. Well, let's components of bone. It's going to be easy, just two major parts. One part is called the organic matrix. That simply means these are the carbon-containing soft components of bone. And it's mostly leather. We call it collagen as a fancy name, but leather is simply woven, if you will, cartilage or collagen. So 30% of the dry weight of a bone, if we had a dry bone, 30% of that weight would be organic. And then 70% of the weight of a dry bone would be mineral. And that mineral, of course, would contain calcium and other minerals as well. And the most important form is hydroxyapatite. That's the hardest mineral in biological systems. The enamel of your teeth is pretty much pure hydroxyapatite, to give you an idea how hard it is. So this collagen, or connective tissue fibers, are woven into the mineral. And when the two are woven together, we get what we call a composite material. That gives it a great deal of strength. You might wonder, how strong are bones? Pound for pound, bones are as strong as cast iron. So thank the Lord for cast iron bones.
But we're glad they're not that heavy, or
That's
it'd be
right.
hard to get around.
To get that strength
Yes.
with light weight, that's the thing that's amazing.
Yes, the lightweight aspect and the strength, bringing those together, is what makes us able to have a skeleton that's so large yet light enough to carry. And then if we look at something like birds, it's even lighter because
Lighter
their bones
yet.
are primarily hollow.
And then just like there's two materials that make up bone, the organic and the inorganic, there are really two basic cells that produce bone. One is called the osteoblast. You see the name here on the screen. The other is called the osteoclast. There are the osteoblasts. They make the material that becomes bone. At first it's soft like plaster, and then it attracts calcium salts from our tissue fluids, and it becomes hard, sort of like plaster becomes hard, more like concrete, I guess, in terms of hardness. So we have cells that make bone. Surprisingly, we have another cell called the osteoclast that removes bone. And you have to do both. You have to make bone and remove bone in order for bone to grow. Let's face it, if you just kept adding bone to the surface of bone, we'd end up with a tiny little marrow space with hardly any blood-making ability.
That'd be a bad situation.
Very bad. Yeah,
So these are going to be our big science words of the day: osteoblast and osteoclast.
Right.
So let's stop and break those words down just a little bit for the folks watching at home. So osteo is the term that we would use to refer to anything having to do with bones.
Right.
So a common disease we hear about is osteoporosis. That's where the bones get brittle and have too many pores in them. So osteoblasts are the ones that build up the bone, and osteoclasts are the ones that tear down. Now there's an allusion back to some church history that we might be able to use there. How does that go?
Well, there was a group of people called the iconoclasts. They were a rather testy lot. They didn't think that there should be any decorations in the church. They were particularly against icons that the Orthodox Church was using. But they didn't like stained glass windows, pipe organs, or really anything else either. So they went into beautiful churches and tore out all of the artwork and all of the statuary, all presumably in service to God. So I'm glad we don't have many iconoclasts around today. But we do have osteoclasts, and it's necessary for bone to be removed too. And that's done by a cell. We put the other arrow on. It's a bigger cell in the osteoblast because it forms from a number of cells that fuse together. We call that a syncytial cell. And the more cells that fuse, the bigger the cell can be. And you'll notice that that cell has just taken a chew right out of the bone here. This is bone. These are the osteoblasts. And so we can remove bone and make bone simultaneously. Our skeleton's actually turning over. They figure in 5 to 10 years, all the bones of our body have completely turned over at least once. So we don't think of bones as being dynamic, but they're changing shape based on how we use our bones. If we float around in space, as some of the astronauts do, bone density becomes very low. When they come back to Earth, get exposed to the gravity again, then we hope most of that bone density is restored again.
And when we think about a young individual, like we've got lots of youngsters watching today, their bones are not fully formed. So we would want to talk a little bit about how that bone growth happens. I think that's what you've got next for us.
Right. The way bones grow is all bones, with just a few exceptions in our body, like our skull is an exception, but all the other bones, all the long bones, finger bones, toe bones, arms, legs, all start out as cartilage. You all know what cartilage is? Just have to reach up here and check it out. We have some cartilage here. We have some cartilage in our nose. Cartilage is flexible. Cartilage can grow from the inside. Cells can, just like in our body, cells can divide inside, and it can stretch to get bigger. Cartilage can also grow at the surface, whereas bone is like plaster. Once it's hard, you can't stretch it. You can't add plaster inside of plaster. You have to just keep adding it to the surface. We call that appositional growth. And the ability to grow inside is interstitial. So both of those are going on. So suffice it to say, we start out with all our bones, with just a few exceptions, being made out of cartilage. Now this is important. Cartilage doesn't turn into bone later. Cartilage is replaced by bone. Cartilage can't stand blood and blood vessels. It's an anaerobic tissue, very unusual for our body. As soon as blood vessels invade, the cartilage begins to break down, and it's replaced with bone. So notice we produce bone in the center. We still have cartilage at both ends. Then we get a secondary center of bone formation in each end, here and eventually down here. And so we have bone at the end, we have bone in the middle, and we leave a plate of cartilage right here. And that's very important. That plate is the growth plate. When you no longer have that growth plate, you can't get any taller. No matter how much growth hormone you might take or get, your fingers can get thicker, but they can't get longer. So we need the growth plate to grow in height. Sooner or later, that growth plate is lost. It's replaced with mineral, and from then on, you've reached your maximum growth and will never get taller. If the growth plate stays active, you can become a giant. You can become, well, at least, well, 7 feet, maybe 8 feet. I don't think we would hold up well if we got too much beyond 9 or 10 feet. So we also leave some cartilage on the end of the bone. That makes a nice, shiny, lubricated joint that's cushioned. We leave a cartilage plate here, at least while growth is occurring. So let's look at that in an actual slide. I'm going to switch this over, and oops, we need to use this one here.
Wrong clicker there. So a lot of the work you did was involved in sectioning tissues and looking at things under the microscope.
Right.
Not the gross anatomy where you're looking at the whole body, but histology, where you're getting down into the tissues and examining
I did
those
teach
things.
gross as well, but
Yeah.
the primary responsibility was called histology, which means the study of things, guess what, that are knitted or woven.
together.
That's what the
Histo
word
is
means.
knitted.
You know what we're going to look at? We're going to look at a foot. This would be a right foot, okay, looking at the bottom, it's a right foot. And we're going to look at this little bone on the end. Doesn't it kind of look like a little hat? Got a peak and brim? That's our distal bone in our toe, and then we have a proximal one. So there's 2 bones in our big toe. All the other toes have 3 bones, but the big toe has 2. Same with our hand, 2 in the thumb, 3 in the finger, so the 2 are kind of homologous. And we're going to see this bone while it's growing. This will be in a foot that is actually less than 1 inch long from a real human baby. It was a stillborn baby, and the foot is less than 1 inch long, probably 5-month development, something in that range. So here it is. Remember, the tip of the bone of the big toe. That's what we have over here on the screen. Here's the tip of the toe. We can get out to the skin. Notice this is real. We're not just looking at pictures now. We got the real thing going.
This is live.
The skin developing out here. There are blood vessels, sweat glands developing in here. And that's the very tip of the big toe. And notice it looks like Swiss cheese, doesn't it? It's full of holes. That's one way to tell bone from cartilage. Cartilage doesn't have any holes because it doesn't have any blood vessels. So look at the cartilage back here. Nary a single hole or blood vessel. As soon as blood vessels do invade it, then the cartilage gets switched on. Okay, so that's how bone grows. The cartilage grows. It makes what we call calcified cartilage, which isn't really bone and isn't really cartilage. It's just kind of mineralized cartilage. Notice the cells kind of swell up. They start tiny and they get big. And then real bone is deposited on the top of this calcified cartilage. It's almost like making a plaster wall. You have to put it plaster on something. You can't hang it in the air. You need chicken wire or whatever. So we have something like that. Now if we go to the base of, or the proximal end of the big toe there, we see there's a joint cavity. The next bone, the proximal bone of the toe, kind of goes out of the plane of section, but notice it is all bone in the middle, but it's cartilage at both ends. Now these little dots we see, those are the bone cells. We call them osteocytes. What they do is they make bone matrix and then they get themselves buried, almost like insects in amber, you know.
Yeah.
That means insects were in the tree sap, they got caught, they got completely buried in the tree sap, and then the tree sap got hard because of fossilization. Something like that's happening, only quicker here. These cells get themselves buried and they're still alive. How would you like to be buried in concrete while you're alive?
Doesn't sound very fun to me.
You better have some channel to communicate to neighboring cells and to blood vessels. So the blood vessels are in these spaces here, and these are the osteocytes, the bone cells that got buried. Here are the osteoblasts on the surface. Let's go to higher power and look at that. There's a lot of interesting things going on right at this particular point.
Now we'll have to refocus now that we've changed the microscope, the lens.
There we go. Oh, better.
There we
much
go.
Better. And remember the two types of cells, osteoblasts, osteoclasts? All these blue-looking cells, they're stained blue, are osteoblasts. So it's making bone all along here, but look at these big cells here. They have several nuclei inside. We can even go up to higher magnification, take a look at those. Those are the osteoclasts. Get our focus going again. Oh, there we go.
There we go. Every time we change that magnification, we've got to refocus.
Retouch it up. It's not quite parfocal. So this is one osteoclast, has several nuclei, and it's just taking this chew out of the bone right here.
That's got a big mouth to take that big bite out of there.
You know, that's what osteoclast means. It means big eater.
Yep.
And so they are a big eater. Look how much this one is eating right there. They say that one of these osteoclasts can keep up with 100 osteoblasts. So the amount of bone 100 osteoblasts can make, the osteoclast can remove.
That sounds like my teenage son and how much food he eats
That's
compared
right.
to my wallet.
I think these cells pick that up from the kids. Now notice here, what is this tissue over here? It stains completely different than this, and there's no holes or vacuoles in it. Even if we look deeper, like this, you see, all solid, no blood vessels, you know that's cartilage. There's no other tissue that could have have an area this big with no blood vessels. So cartilage is anaerobic. That means it gets along just fine without
Doesn't need a
oxygen.
direct oxygen supply.
Right. In fact, cartilage actually makes a chemical called anti-angiogenic factor that goes out and chases the blood vessels away. So as long as they make that factor, they stay free of blood vessels. But when blood vessels start to invade, then you can get a switch over to bone. Well, let's go back to our
Just switch
microscope
back to
here now,
the screen.
or the screen. And it takes a
Now.
little while for it to figure out how to do that.
There
There it
we
is.
go.
And here you can see how this bone grew from the dotted line right here. Let's say it was this size at one time. Here it is over here. And it grew from this to this. To do that, what did it have to do? It had to get rid of bone here, erode this away, and it had to add bone here. So you see, you have to have a bone remover and a bone maker to keep shaping the bone as it gets larger. There's a disease called osteopetrosis. What happens, this happens in young children. It's a terrible disease. It's a birth defect, really. And you have the osteoblasts, but you have no osteoclasts that are working. That means you can keep making bone, but you can't get rid of any. And so the bones become extremely dense, and they don't become that much stronger. They just become heavier. And what's the biggest problem of all? Very little space for marrow. So these children will be anemic if this isn't solved.
Because the marrow is responsible for producing the important cells of our body that carry the oxygen around.
That's right.
Those cells that are the hemoglobin producing cells in your blood. And
White blood cells and the red blood cells. The white blood cells are involved in immune reactions
response.
and getting rid of bacteria and unwanted materials.
yeah, so marrow is an extremely important part of our bones.
Now, we can get taller and taller.
Even as tall as me.
Right.
I'm only 5'19", but
Yeah, I made it to about 6'1". You made it a little further
a
than
little
that.
further.
That's because Mr. P's growth plates were active a little longer than mine. They were available. But eventually those growth plates, and you can see a picture of them here on the screen, this would be down at the foot. This is the ankle right in this region here. And this is the tibia and the fibula, the two bones below your knee. And this little space right here is a growth plate. Notice you have one for the fibula and for the tibia. And this is what it looks like in the microscope. This is a little vein of cartilage. It can continue to divide, but as it divides, it breaks down, it dies, it forms calcified cartilage, and bone is deposited on the surface of that. And then from then on, it's just bone on top of bone on top of bone. But you always have the option of an osteoclast removing some.
Yep. And the fancy name we call that is the epiphyseal plate.
Right. That's because the end of the bone is called the epiphysis. That's called the epiphyseal plate.
So if you've ever broken your arm or your leg or your wrist and you've gone in and had an x-ray, the doctor may have told your parents, well, he's still got room to grow, because they can look at that in the x-ray and see that gap and know there's still growth happening. If it's closed up, they'll say, well, he's done growing and you're not going to get any taller.
Now this is a real human femur. It's about my size. If I ever need one, this is going to fit just perfect here. And this is probably from a person about my age, 39.
39, yes, exactly.
And it's been sawed in two so we can see where the marrow used to be inside. But what I want to show you in particular here is down near the knee. You see this little line here? That used to be the growth plate. That growth plate was cartilage. It allowed this person to get this height, this length. But at some point in his life, the cartilage was all used up, and only bone was left, and now growth hormone will not make this individual get taller.
So if we think about this matrix in here, this hollow cavity that you can see down the middle, that's where the majority of the marrow would be in our long bones, in those central sections. So if you've ever taken a chicken thigh bone or something and snapped that in half, that dark material inside of there is the marrow section.
Now here we're going to get really technical.
All right.
You see this compact looking bone here? Real compact. That's called compact bone.
Okay.
Now I want you to take a stab what we call this spongy looking bone up here.
I think you gave us a hint.
I think so too. Yeah. That's spongy bone. Isn't that a good name for it? Now you might wonder, well, why have spongy bone? We have compact bone. It's a nice tube. Tubes are very strong. They resist bending, unlike a rod if it was all solid.
Yeah.
But these little beams are important because they can change their orientation very quickly. Osteoclasts can dissolve those little beams and put them in a little different angle. So if weight on our limbs, say a lady becomes pregnant, has 20 pounds of weight out here she didn't have before with the amniotic fluid and everything, the bones of her hips and her legs and everything will all remodel. These little beams will all adjust a little different angle to best support that baby. And as soon as the baby's delivered, they all get remodeled back to where they were again.
So God's given us a design that helps us modify our bones while we're growing, while we're living, based on the different types of activities that we do.
Absolutely. Now I'll show you what those little beams do for us if we look at our picture over here. That's the growth plate that has been mineralized. And you'll notice that the beams are running perpendicular. This would be our knee joint, so the foot is up that way. This is the knee joint. Notice these beams of bone, we call this spongy bone or trabecular bone, are perpendicular to the forces that are coming to bear there. Even on the side, they run at an angle that is appropriate to give the most mechanical support. Now, why not do this with all solid bone? Why do it with these little beams? Oh, is there a good reason for that? I'll give you a little picture that I think you'll find memorable. I got a shelf to put my books on, and when I got all the books on the shelf, guess what happened to the shelf? It did that. So I solved the problem. I cut off another piece of wood, the same material as on the shelf that was bending. I cut off one more piece of that material, and I put it perpendicular under the middle, and now it supported it. So you see, a board can be bent sideways, but end on, it's much stronger. And that's why these little beams, these trabeculae and spongy bone, are oriented just like that prop on the shelf. It wouldn't do any good if it went crossways. Or even if it was at an angle. It would not give us the support. It has to be perpendicular.
Right at that angle.
And this is dynamic because bones are alive. This is changing dynamically in your life. I mean, if you had a stone in one shoe and you were silly enough to leave it there, and then you walked kind of limping, the bones of your legs, particularly the spongy bone, would all readjust to best accommodate your foolish manner of walking.
Yes, they'd start readjusting. And that can happen too for people who have limbs who are slightly different lengths, or they have an accident or injury that causes some type of limp like that.
Now, what does a compact bone look like? I saved the best for the last. Wait till you see this. This slide, what we did here was to take a human bone, cut across this way, get as thin a piece as we can of compact bone. We still can't get light through that, right? So what we do is we put it between two grinding plates with grinding compound, and we grind it until it's so thin light goes through it.
Okay, we call that thin sectioning is the term.
Right, only this is a hole mount, and right on this slide now is a little white fleck on there. That is a piece of compact bone that's been ground down so thin we can shine light through it. And when we shine light through it, we're going to see something amazing. Because this model pretty much shows us what we're going to see. This is the outside of the bone. This is the marrow over here. And the bone is organized as cylinders of bone called osteons. And a blood vessel runs right through the middle. And the cells are buried. Remember, the osteocytes are buried in bone, but they're buried in concentric circles. And the collagen fibers are woven so that they're in different planes, just like in plywood, to give it strength. This is why we get the strength of cast iron with such light weight. It's the weave of the collagen fiber with the mineral of the bone makes it so strong. Now, how did you get the blood vessel in there? How did you get the cylinder in there?
We didn't make a drill and go all the way through there.
There was a drill.
Oh, there was a drill.
The drill is called the osteoclast.
That's
Remember
that
the one
living
that can
cell
keep up
that
with
keeps
100
eating through.
osteoclasts? The osteoclast literally will come along, like maybe the next one will drill a hole right here. And so we're going to have a new hole this big around, and it'll go, it cuts so fast it's almost visible, osteoclast. It'll cut that hole for some length down the bone. A blood vessel will drop into that hole, and then the bone will build layer by layer.
Right around the
starting from the outside, because remember you have a big hole there now, blood vessels in the middle, and it grows in. We call that centripetal growth, not centrifugal.
Yes.
So now we're going to look at this in reality, and this will be your reward for paying such close attention here today. Get down to lower power. And we'll get the bone under here.
There it is. Find some focus.
And get some focus on it.
There we are.
Now look at all these holes with rings around them. I'm going to take that one right in the middle, right here. You see that? Just like we saw in the model. I'm going to magnify that until we can see the osteocytes. This is where the blood vessel used to run, in the hole in the middle. So that hole was drilled by an osteoclast. And then the cells that make bone start at the periphery, and they move in, layer by layer, just like plywood, running the fibers a different direction in each layer to give it strength.
We come up another layer of magnification there. So we're going in a factor of about 10 times each time we go in here.
Yeah, we went from actually
Is that one a bigger jump?
3.5 to 10.
Oh, okay, so a lot more, 3.5 times.
So now we can see the layers. This is like plywood. Each layer, the fibers are running in a different direction to give it strength. The blood capillaries used to be right in the middle. And the idea is all of these cells set in little holes called lacunae, which is like being buried in concrete. And if you're buried in concrete, how are you going to get your food? How are you going to get the water? That maybe went from your mouth or nose through the concrete to the outside world, and you could bring in the nutrients that way. Oh my goodness, that's what we have. Let's crank up the power some more. So we're up to 400 magnification just on the microscope, and that's much higher.
Plus we have whatever the camera's giving us on the screen.
Now you can see, doesn't that look like spiders? There was a cell called an osteocyte right in here. It was alive. It needed to get its nutrients from the capillary in the middle. And there's little tiny pores or holes that go through called canaliculi, meaning tiny canals. And the little cell processes go through these canals and they pick up the nutrients. And this cell sends it to the next cell. The process of the next cell comes in and meets this one tip to tip inside of the canaliculi. And so the nutrients go from cell to cell like a bucket brigade all the way out to the periphery. There's a limit to how far this system works, so there's a maximum limit to how big an osteon is. I don't care if it's in a dinosaur or a human. And by the way, a dinosaur would look exactly like that, the compact bone. It would have osteocytes, it would have canaliculi, and it shows homology. God has a plan that's used across the board in all vertebrates.
All right. So God's made these things in amazing ways. And would you, thinking about this from a biblical perspective, you understand that God has formed these systems and these structures to function the way they do right from the beginning. From an evolutionary perspective, you taught alongside evolutionary colleagues for your entire teaching career and working in other areas as well. How do they come up with an explanation for something that's so amazingly complex and appears to be clearly designed, but isn't?
Well, you know, you can teach the whole course, any course in the medical school, without getting involved with evolution. I never bothered to bring it up, and I never received a single bit of criticism for not bringing it up, okay? In fact, I won several awards for the teaching. But some of the faculty would mention it. So in the middle of a lecture, they'd maybe take 2 or 3 minutes just to talk about how maybe the kidney evolved, you know, a little speculation. It was fun to watch the students. I was a course master, so I was at all the lectures, and I'd see the students from behind and could see the speaker up there. The students would be taking notes on, say, that kidney. And as soon as the prof would start talking about how the kidney might have evolved, they set their pencils down, relaxed, glad for the break. They weren't being disrespectful. They practically all believed in evolution, but they knew 2 things. 1, this isn't going to be on the exam. And 2, they'll never use this in the practice of medicine.
When they get into the office and are treating patients, there's not much of that involved.
I've had several of my former medical students come to the Creation Museum with their families, and I always ask them, have you been able to teach or practice medicine without evolution? And they all laugh. I just get a laugh. I mean, it's like a funny question. The answer is so obvious, you laugh at it.
Yep. All right, we've got one question we're going to answer to wrap up the show today. Morgan, who's 11, one of our regular viewers, she asked, where did you get the toe bone that you showed us the section of before? Now, you mentioned that had come from a stillborn baby. So a lot of the tissues and things that you've worked on, especially for things of that age, how does that come into the scientific medical community to be able to be shared and studied?
Well, of course, they would ask permission if the baby could be used for, you know, research purposes and study, and sometimes that permission would be given and sometimes not. Most of these slides were made years before I got involved there. They were made, these are not slides you buy from supply houses. They're made in-house by lab techs, and most of our slides were of that nature. So I don't really know the source, the details of the source for really any of my slides. The other thing, at least half of the microscope slides that our students looked at were not human. They could be dog, they could be cat, they could be rat, they could be mouse, they could be chimp. And what does that tell us? It tells us that there's an underlying similarity, we call it homology, runs across all creatures. So you can study a kidney in a rat and learn quite a bit about the human kidney in the process. Imagine if God had made every animal completely different. So cats have DNA, but dogs have BLR, okay? And humans have XYZ, totally different genetic mechanisms. We have kidneys and livers. Let's say dogs, cats don't have anything remotely like kidneys or livers. Some other system. We have blood, they have something else. We have hemoglobin, they have something else. That would be so chaotic. Anything about the human body or apply it to the human body in the way of experimental surgery, medicines, what have you, everything would be totally unique. But instead, God has given us this underlying theme that allows us to benefit from the study of a mouse and apply that knowledge to a human, all without ever considering for a second that the mouse is really just a made-over human.
Yeah. All right, so that's a little foray into bones. And of course, as we always say, there's so much more to learn and explore and understand about these things. And as you are growing up and going on and studying in high school or college, opportunities abound to find out more about these amazing structures that God's created in our body. And until we see you next time, get out and explore all of God's amazing creation.